This is our final presentation for ME452 by Team 10. The part that our team chose for redesign was the coffee pot, which is a device that allows for freshly brewed coffee in various serving sizes. This product works by heating water from a reservoir and then dripping the hot water over coffee grounds into a filter basket, thus extracting the flavor into a pot. Primary customers include office spaces and various event spaces, as these office spaces and event spaces, such as restaurants, boutiques, hotels, also seek to provide their customers with quality and efficiently prepared drinks. Secondary customers include individuals who are frequent coffee drinkers, and these individuals who buy coffee pots for their households prioritize quality, cost, and ease of use.
The task function of the coffee machine is to brew the coffee. Its primary basic functions include filtering the coffee, dispensing the coffee, as well as maintaining coffee temperature. The primary supporting function is to make sure the process is convenient and dependable by limiting temperature. Additionally, the machine enhances the product by reducing noise and please the senses of the owners by improving in aesthetics.
Getting into the function component mapping matrix, it shows us the primary functions and secondary functions of most of the parts in the coffee system. And from this, we can see which parts have similar functions and use that to inform our design modifications as well as optimizing the overall system.
Now to talk about product family design. The function that differs between our two customer segments is control volume. This is based on the idea that customers who use this machine in communal places such as offices will want a larger amount of coffee stored in the pot compared to individual users of the machine. On this basis, our modules are the components within the kettle subassembly, the pot lid, and the kettle body.
For the design for manual assembly, we choose a part to redesign based on the core chart, but most of the parts that is high manufacturing costs are purchase parts, which we cannot really redesign. So instead, we choose other parts to modify so we can really reduce the cost. So for the platform parts, we combine the container lid and water tank lid into one big lid, so we can reduce part count, allow hand and tool access, and reduce part variety and also increase part symmetry. And for the module part, we redesign the kettle strip so we can reduce part count, redesign fasteners, and also we turn it into a snap fit. And also we can avoid tangling by modifying the geometry. DfM modification, we reduce the assembly time by 41.4 seconds and also increase the assembly efficiency by 0.9%, where we also maintain all the product function and also reducing the manufacturing cost by reduce the number of parts and fasteners.
The redesign for automated assembly focuses on parts that were both high in terms of functional importance as well as manufacturing cost. This intersection helped us choose the heating module and the heating plate for redesign. The heating plate is held in place by a set of 5 plastic plate holders which screw directly into extrusions that rise from the outer covering of the machine. A cross-section view of this part is shown on the left in the slide. We specifically redesigned these plate holders to preserve the form and functionality of the original but do not require screwing in. The new design locks directly onto the outer shell by means of a female opening built into the structure. This reduces the overall part count for our selected subsystems by eliminating all fasteners required in the original plate design. Our DFA analysis for the assemblies, both pre and post the redesign, are documented in these tables shown. The newly designed plate holders, which we talked about in the previous slide, help reduce the overall part count from 11 to 6, which in turn drops the total assembly cost from $10.51 to $6.44. This is a 40% reduction, which we consider substantial.
The new design combines the water and filter tank lid into a single polypropylene unit. The material was chosen for its low density and toughness. The critical feature is the hinge. To guarantee smooth motion, we tightened the tolerance to plus or minus 0.25 millimeters rather than standard tolerance of plus or minus 0.5 millimeters. After evaluating our options, injection molding was the only process capable of meeting our geometric, tolerance, and production volume requirements. Using the parting surface defined at the end of the lid, the initial injection molding cost was estimated to be around $1.25 per part. The design at the stage had a volume of approximately 64 cm cubed and a maximum wall thickness of 3 mm. This thick region occurred at the hinge to provide structural support, but it created a significant significant non-uniformity that would lead to uneven cooling and longer cycle time. Running the model through DfM Pro highlighted several manufacturability issues, including insufficient draft angle, non-uniform wall thickness, and localized overly thick sections. Based on the feedback, the part geometry was modified to reduce wall thickness, ensuring uniform sections, and introduce proper draft angles. The hinge region was redesigned to increase structural stiffness while eliminating excess material buildup. Sharp internal corners were also softened to improve flow and reduce stress concentration. These changes reduced the maximum wall thickness from 3 mm to around 2 mm. As a result, the part volume decreased slightly, cooling time improved, and both operating and mold costs were reduced. The updated cost estimate was $1.061 per part, representing a saving of approximately $0.2 compared to the original design.
Getting into the process selection for the kettle strip part, the key dimension for this part is the positioning of the two holes, which is required for snap fitting with the kettle handle. And the tolerance for this we chose to be 0.2 millimeters. We also chose aluminum alloy to be the material for this part due to its lightweight non-rust properties. And from our process selection analysis, we determined sheet metal work to be the ideal process.
Here you can see our initial design for the kettle strip, which we determined to have a cost per part of 1.338 cents using the analytical method for sheet metal working. Some of the key part specifications are outlined here as well, and once we did this, we then analyzed the part using DfM Pro. With this, we got that we had no recommended improvements, so we individually identified 3 features to modify based on the DfM guideline. Even though DfM Pro gave us no recommended improvements to our design, we identified 3 aspects of our design that we felt could be further improved based on the following design for sheet metal guidelines. These guidelines were number 6, which is to avoid sharp corners, number 9, to avoid sharp bends, and number 10, which is to avoid small holes or too close holes. Following implementing these redesigns, we recalculated a new cost per part, which we determined to be $1.96, saving an overall of 19.2 cents per part. Pre and post DfM designs were quoted online through hubs to compare with the analytical method. The key takeaway is to note that both the analytical method and the online quote from hubs show an increase in cost after the modifications made from DfM. It is also important to note that the cost per part based on the hub's online quote is based on aluminum 5052 instead of aluminum alloy 3003 that we selected for analytical calculations earlier in the process. Likewise, there is likely to be some additional error given that the cost from hubs was extrapolated from 50 to 200 units, which is significantly less than our estimated volume of 17,480 units.
Our proposed product service system is called Daily Brew. Its goal is to enhance user experience and extend the product's lifespan without having to add complex or costly hardware. The system centers on a user-friendly app that provides advantages in personalization, maintenance support, and consumable management. Users can track brew cycles, monitor preferences, and receive custom recipe recommendations using low-cost Bluetooth or QR code interactions to connect with the coffee machine. Daily Brew also offers maintenance reminders and step-by-step guidelines without relying on a lot of new sensors for tracking. Moreover, optional subscriptions for coffee beans, filters, or descaling solutions can further be an opportunity to add convenience and create additional revenue for this product. Together, the modified coffee machine accompanied by the Daily Brew service platform can form a well-integrated system that not only improves usability and value, but also keeps the product affordable. In conclusion, our redesign successfully met the goals of simplifying assembly, reducing cost, and improving manufacturability. By reducing the part count and using snap-fit features, the manual assembly time was dropped from 309.65 to 274.26 seconds, and the efficiency was increased from 17.7 to 18.6%. Automated assembly costs also decreased substantially. Designed for manufacturing improvements such as combining the water tank lid and filter lid into one optimized molded part helped us reduce both material and tooling costs. Metal components like the kettle strip were redesigned using sheet metal forming to achieve tighter tolerances and simpler tooling. Regarding opportunities for more improvement, they include simplifying complex molds, refining interfaces between major components, and further evaluating long-term durability and ergonomic designs. Finally, by integrating our Daily Brew service system, It enhances the user experience and the brand engagement while maintaining the manufacturability advantages we achieved from our redesign.